Okay, welcome to the next data journalism lab. In this lab, we are going to continue doing many of the things that we have done in previous labs, working in R Studio, loading and cleaning and making sense of and analyzing data using the Tidyverse framework of packages. We're going to create some new columns in our data set. We're going to do some summarization. We're going to store it on GitHub. Today we're going to do two new things, which is we're going to learn how to put together or join together two related data sets on a common field, which will allow us to do some new kinds of analysis. These are called joins. We're also going to discuss some common problems that arise when doing joins. This is an area where people can get into a lot of trouble unless they really know what's happening, and so I want to go through some of those things. We're going to start, though, by doing some additional data cleaning, including fixing some dates so that we can work with them. You'll probably remember in past weeks, the dates of each shipment have been stored in a weird format, and that's prevented us from doing any real kind of work. So we're going to clean that up and then just do a little bit of work with them. So this lab is the same as all the previous labs in that you're going to listen to me, follow along with the R Markdown file, and you're going to run the code that I'm running, listen to me explain things. Occasionally you'll be asked to do something where you'll see the word task. Ultimately, when you're finished, you should save your R Markdown file, knit it as an HTML file, put it in your Git repo using GitHub Desktop, upload it, and then upload those changes, the links to Elms. There's a bunch of information here you can use to get help as you're doing this. This is all the same as before. There is one new thing I just want to flag, which is information about a package we're going to be using today called Lubridate. Okay, so just to set up, hopefully you've already done this, but you are going to download the zip file from my Git repo, put that on your desktop, create a new folder in your GitHub repo and move the file in there, unzip it, open this file in RStudio, rename it to include your name, and then create a new R project inside of the folder, which will, again, set the working directory into this folder. Okay, so we're going to start, as we always do, by loading packages. I'm going to want you to load the Tidyverse. I'm going to want you to load Janitor. Remember, the Tidyverse is for all kinds of data science goodness. The Janitor package does some cleaning. We're also going to install and then load a new one today called Lubridate. So I just want to open this up. So Lubridate is, it's in the Tidyverse family, but it is not part of the core Tidyverse, and it's all about working with dates. And there's a great cheat sheet for it that will show you, allows you to convert dates and do all sorts of things. So we're going to be using that today. So first here, you're going to create a code block right here where you're going to install Lubridate if you need to. You're also going to load the Tidyverse, you're going to load Janitor, and you're going to load Lubridate. So go ahead and do that and run that now. Okay, so for this exercise, we are going to be doing working again with opioid data, which we have been all semester. The folder that we're working with, mostly in previous labs, we've been working with a single spreadsheet. We're actually going to work with multiple spreadsheets today. We're going to start with the subset of shipments between 2006 and 2012 to Mingo County, West Virginia. It's one record per shipment. Includes information about the number of pills in that shipment and the pipeline from the manufacturer to the distributor to the pharmacy where those pills went on which date. So we're going to start by reading that in, which I'm doing here by running this code block here, storing it as an object called Mingo. I want you to use Glimpse and View just to get a sense of this data. So go ahead and put those in here. Remember, this is a critical step to make sure we know what we're looking at, how things are stored. I'm just going to go ahead and do that here. You should do that on your own. One thing I want you to pay attention to here that we haven't used a lot of is this transaction date field. So here it is, right? Stored as a character, and this date, 01/04/2007. This is January 4th, 2007, but it's not really ordered in a structured in a nice way. It's also stored as character, not date, and that makes it hard to do things with. Some basic data cleaning tasks that I want you to go ahead and do. The first is I want you to execute the janitor function in this code block here that will take all of the names which are uppercase, right, or capital case, and convert them all to lowercase. If you can't remember how to do this, look in a previous lab or look it up online, but there's a single function. You're going to want to store the changes as Mingo, because otherwise these functions that come later on aren't going to work exactly right. So go ahead and do that now. Okay. So at the moment, the date column is a little bit unusable, right? It's a string of characters in which the month, day, and year mash together. And as I pointed out, this is what January 4th, 2007 looks like. 01/04/2007. In order to make use of it in our analysis, we need to sort of restructure it so it looks like a real date and actually have R pick it up as a date. And that's where the Lubridate package comes in. And I provided a link here, but I highly recommend this cheat sheet. There's a cheat sheet for the dplyr part of Tidyverse and the reader package. This is for Lubridate. We'll walk you through. We're going to just barely scratch the surface of what this package does, but it allows you to easily calculate like the difference number of days between two different dates. It allows you to convert dates in weird formats. I can't understate or overstate just how frequently fixing dates or making dates workable comes into play when we're doing data journalism. We work with a lot of time series data, and it's just critical to have them in a format that's actually usable. So yeah, Lubridate is great. So I just want to show an example of a bit of code here. We're going to take this really messy transaction date column, which again is just a string of characters, and we're going to turn it into a valid date. And so to do that, what I'm doing is I'm saying take Mingo, the data set called Mingo, and we're going to store the changes that we're going to do here as Mingo. So we're essentially just overwriting what we're doing. Using mutate, which as you remember from previous labs, allows us to create a new column. So I'm creating a column called transaction date, which, as you'll probably notice, is the name of the column that is currently in our data set. So what I'm doing is I'm basically saying take the existing column and change it and just overwrite those changes. So there's a function here, part of the Lubridate package, called MDY, and you can see it here. This is a parsing a datetime function. So what it's doing is it's essentially saying take something that is sort of vaguely structured as month, day, and year. So in this case, we've got we've got the month, then we've got the day. So month is 01, day is 04, year is 07. Take that and turn it into a valid date. And then I'm just reordering the column so we can put it up front so we can have a look at it. So I'm going to run that and then load it. And so now our date, instead of being stored in that really sort of funky 01/04/2007, actually looks something closer to like a valid date time thing. And if we glimpse it, we can now see that this column is something that R understands to be a date. So here is the transaction date. Instead of CHR, which stands for character, it now says date, and you can see all these are in sort of a valid date time format. Okay, so now that we have it as a valid date, we can actually do things with it that make sense. So let's say we wanted to sort this from the highest, sort this from the earliest transaction date to the latest transaction date. I can just use the arrange function. So I'm taking my Mingo data set, arranging by transaction date. And now we can see it's ordered starting the 2nd of January 2006, and 3rd, 4th, so it's in order. If we tried to do this previously, it wouldn't really work. It would sort all of the Januaries together, so 01, and then all the Februaries together, regardless of year. So it wouldn't work as we expected it to. We can also filter. This bit of code below filters just for shipments on Halloween in 2006. So what I'm saying is take the Mingo data set and filter it where the transaction date is equal to 2006 10/31. This as date function that the thing I'm filtering on is wrapped in is also part of the Lubridate package. So anytime we're filtering by it, we put that instead of just the filter, instead of just the number, just a little quirk of Lubridate. We can also use additional Lubridate functions to extract additional information from a valid date column. So the function below here extracts the year from our transaction date column, and then creates a new column called transaction year to store it in. So what we're saying is create a new column called transaction year, and what do we put in it? We put the year inside of the transaction date. So year is a function that is, and you can see it right here, year is a function within the Lubridate package that extracts the year from a valid date. And then this last part, I'm just reordering the columns, so when we look at it, we can see we've got the transaction date. In this column, it's stripped out the year, right? 2007, 2007. This is a date in 2008. This is in 2008. Okay. And then once we have that year, we can do more operations to it. So let's say we wanted to look at how the number of shipments in Mingo County changed over the course of the year. You know, were there more in the beginning and less at the end? Well, we can answer that by starting with Mingo, our data frame, and then grouping by this newly created transaction year column, and then creating a summary column, right? Essentially a pivot table in which we are summarizing the total number of shipments for each year. So remember, the n function is essentially a count. So it's the number of rows in which the transaction year is 6 or 7 or 8, 9, 10, 11, and 12. And what do we see? We see that the overall number of shipments started lower in 2006, spiked in 2008, fell a little bit in 2009 before falling off again in later years. So we could build some reporting around that and try and figure out why that happened. Okay. So we're going to wrap up this date section and move on to joins here, but I want you to do something now. I want you to create a code block below that looks much like this, that answers the following question. How many total pills were shipped to Mingo County each year between 2006 and 2012? And then in a comment, I want you to explain what the overall trend was during that period. So it's going to look a lot like this table, but instead of total shipments, you're going to have the total number of pills for each year. So this is actually a very common question type we've asked in previous labs in which we've grouped by something and then totaled up the number of pills. And I want you to figure out or refresh yourself how to do it, but go ahead and create a code block right here where you do that. Okay, next we're going to talk about joins. So joining is the process the term we use to refer to the process of putting together 2 or sometimes more than 2 data sets. This is an extremely common technique that comes up all the time in data journalism and data analysis, and there are a few reasons for this. Sometimes we are working with a single data set, and generally when we're talking about this, we're referring it to a database in which information is split into multiple tables. And then in order to answer questions we might have, we need to find a way to combine information from two of those tables into a single thing. So that's a very common thing. You have a single data set in which the information is organized into multiple related tables. And we'll look at an example of that in a second, much lower. Another example is we might want to work with 2 seemingly unrelated data sets and combine them together to learn something new. And this is where, sort of your reporter instinct or things sources have told you or ingenuity comes in. In the business, we often call these enterprise joins. In the same way we might call like a story that isn't some kind of breaking news thing, but is based on some original reporting on your part where you're getting information or thinking about something in a way that is unique. Not a story that's sort of handed to you necessarily, but something you're coming up with on your own. In the world of data journalism, we often call this enterprise joins because we're taking 2 maybe unrelated things, putting them together to create some kind of new information. So examples of this are examining lists of bus drivers for criminal records, or as we saw in our classwork, looking at the relationship between the death rate from opioids and the number of opioid shipments that the Post did. These are very powerful tools, and it's really good to sort of get in the habit of thinking how I can put 2 things together. So we're going to do an enterprise join right now, and our goal is going to be to answer this question, right? Which U.S. county or area of the country received the most opioids per person per year on average between 2006 and 2012? And so to do that, we need to put together 2 data sets. So the first data set that we're going to load in is something I pulled together pulled down from a repository the Post is set up for accessing this opioid data. And then I did some calculations to it. So it's in the data folder. So if you just run this code below, we'll load it, and then we're going to take a look at it together. So I'm calling it county pills per year. So let's go ahead and pop that open. And I'm just going to open this in a new window here. Okay. So what are we looking at? So for each county in the U.S., and in some cases it's actually like a city, but we'll see that a bit later. We've got the county FIPS code, which is a unique identifier that is you'll see actually in like a lot of different data sets for each county. Then we've got the name of the county, the state, and the average number of pills sent or received by buyers or pharmacies typically in that county each year between 2006 and 2012. So the original data had a value for each county for each year. I just averaged this together to get the average amount per year. Okay, so we can see here we've got 3,130 observations in our data. Just scanning down, you'll see that it looks to be like pretty complete. There aren't a lot of like NA values, and we've got typically 1 per county. Just want to get to the bottom here because I want to show you something that's going on with this data set that may make it sort of a little bit tricky to work with, and things we should be thinking about. Okay, so we get down here in rows 33037. So if you're not there yet, go ahead and scan down. And you'll notice that the county FIPS code and the buyer county are blank for a bunch of rows. And but the buyer state is not, and we have average pills per year. So in this case, what we're looking at is this would be like transaction in California from the original data set, which actually didn't have a county linked to it. So that's a potential issue there. And then we've also got a bunch of data for which there is no county FIPS code, but there is a county name and a state. So these are, jurisdictions in Puerto Rico, but there is no corresponding county FIPS code. We've also got VI is the Virgin Islands. I'm not sure what PW is, or that's Montgomery, Arkansas, but it doesn't have a FIPS code. So just a couple things to note, but there are 3,130 observations in this data. I just want you to keep in mind for later that, and this will become important as I explain what joins are, where that we're missing some information in some of these columns. Okay. The second data set that we're going to load has the average annual population for each county between 2006 and 2012. So I'm just going to go ahead and run this, and then we're going to open it up, and I'm just going to pop it out so we can look at it separately. Okay, so this also contains some of the same columns. We've got a county FIPS code, which again is labeled the same thing in our other data set, and it's a unique identifier for each county. We've got the county name, the county state. We've got the average population per year. So this I calculated. I had the population for each county for each year between 2006 and 2012, and I just computed the average into this data set. So that's what you're looking at here. All right, so we have 3,143 observations. Just note here that this is actually different than the number of records in our pills. That's going to come into play when we talk about how joins work in a bit. And let's just scan down. And what we see as we go through this data, and you should be doing this too, is that it's complete across the board. For every single county listed here, we've got the FIPS code, the buyer name, the county name, the state name, and the average population. Okay, so again, different number of records, something to keep in mind for later. Okay, so here's what we're trying to do next, is we want to take the two tables, this pills table and this population table, and we want to put them together so that we have the name of the county and the information about the number of pills and the information about the population together in one single table. So that then we can do a calculation where we figure out how many pills per person went to that county. So anytime we're doing joins, it's really, really important to remember that the joins really only go into work if there's at least one column in which there is kind of the same information or most of the same information in one column in one table as in one column in another table. So when we do our join in this case, we do have, we are fortunate enough to have this unique identifier, county FIPS, which is standard for each county in our pills per year table. And we have county FIPS in our population table. We are going to do a join using that county FIPS column. These happen to be the same name, which is really helpful. It is possible to join columns when they are different names but have, sort of equal values in them. But it's not required. What is more required is that the the columns both have the same kind of information. Okay. We're going to see later, too, why we're doing this join based on the county FIPS column and not the state or the county name. That's going to cause problems, or would cause problems, and we're going to look at why a little bit later. Okay, so we're going to run some code below in a second. I just want to describe it. What we're doing is we're creating a new table called Pills Population, and we're going to put these two tables together. Using the county FIPS code as the unifying field. So what I'm saying is take the county pills per year table, inner join it, and there are other types of joins. We'll talk about those in a bit. We're going to inner join it to the county population per year table, and the column we're going to use to join in both tables, it's called county FIPS. Okay, so I'm going to run this. We get this new table here called Pills Population, has 3,036 rows. Note that that is less than our original population table and our pills table, and I'll explain why that's happening in a second. Okay, let's go ahead and take a look at the table that it returns, and I'm just going to pop this out so we can see it. Okay, so what are we looking at here? So it returned first the column that the two tables share that we asked it to join on. So county FIPS, right? Then it returned the city and state, which was contained in both of our tables. So this one, Bexar County X, Bexar State X, is that information from our pills table. And then Bexar County Y and Bexar State Y returned that information from our population table. And then it also pulled in the average pills per year from our pills table and the average population per year from our population table. So behind the scenes, what was happening was we started with a table that looked like this up to here, right? This is our pills table. So R took this FIP code, 01001, which is the FIPS code for Autauga, Alabama, and then it went looking for that match in the other table, and it found it. And here was the information in that other table with that same FIPS code. So it took that and aligned them together. Okay. So I want to clean it up just a little bit using the code we have below. All this does is just makes this a little bit more readable. So what we're doing is saying take the pills population table that we just created. We're going to select the county FIPS code, only the Bexar County and the Bexar State from the pills table, that's the X here, and then the average pills per year and average population. And then I'm just going to rename the county.x and state.x columns to remove the X's. And when I run that, now we have only 5 records here. Our table looks a little bit nicer. This is what we were after. We've got the county FIPS code, the Bexar County, the Bexar State, and then pills per year and the average population per year. So we are dangerously close to being able to do our pills per person calculation. So we're going to do that in the code below. So this code block below creates a new column, and we're calling this new column average yearly pills per person. And it calculates this, what we're going to put in this field, by dividing the average pills per year, so this column, by the average population per year, this column. So average yearly pills per person is the average pills per year divided by the average population per year. Now I'm just going to kind of, with this part of the code, just clean things up a little bit. So we're selecting, first we're putting the Bexar County and the state. We're putting this new metric we just created. and then we're putting the additional information after that. And I'm sorting from highest to lowest so that I can create a table that will allow me to see kind of the highest information. Okay, so here's what we get. Norton City, Virginia, which is actually a small city inside of Virginia. Virginia has this weird thing with jurisdictions. There are some cities, some counties, which has the highest average yearly pills per person, 305. So does Charleston, South Carolina is up there, and Leavenworth, Kansas. As the Post is reported in some of their docs, this is probably because of the location of some very large pharmacy distribution facilities that happen to be there. Another thing we also noticed that pops out, 4 out of the top 10 are in Kentucky. And there's a couple other big ones, including Mingo, which is one of the ones we've been looking at throughout our time in this class. Okay, so hopefully that didn't seem too bad. This was a pretty straightforward example of a join. There's a lot more going on with joins. Joins are really powerful, and they allow us to do some pretty amazing things in journalism. But they're also a place where you can get into a lot of potential problems, which is why it's really good to have an understanding of how joins work exactly and how they can go wrong. Otherwise, you can end up drawing inaccurate conclusions. So I want to talk a little bit about different kinds of joins and maybe answer some of the questions you might have had about why we were getting different numbers of records as we did this join above. Okay, so as I pointed out, there are several different types of joins. The dplyr reference that's linked to here goes through how to end up writing some of the different functions. So we'll talk about inner, left, right, full in a second. And again, the cheat sheet has some great information that you can find where they talk about joins, different methods of doing joins. Okay, so the one we did above was called an inner join. And an inner join is a unique type of join. It's probably the most common type of join. And what it does is it puts two tables together based on a shared column. And it only returns a row if there's an exact match in that column in both tables. So a very common way that we can visualize how different types of joins work are with Venn diagrams, which are composed of overlapping circles. So here's just an example of what I'm talking about. So here we can see we've got two overlapping circles, each one representing a table. So this is table A, and this is table B. In this case, this might be our pills table from the example above, and table B might be our population table from above. So when you do a join, R needs to figure out whether it's going to return a record. And whether it returns a record in your new join table is largely dependent on the data, but also on what kind of join you do. So when we do an inner join, what we're doing is we're only returning a record if it falls in this part where the two tables overlap. So if there was a county FIPS code that was in our pills table, and there was a corresponding match in our population table, then it would return the record. And vice versa is also true. But if either one didn't have it, it's going to leave that record out. Okay, so when we looked at our combined table, it had 3,036 observations or records. This was the pills population table we just created. Our pills table had more than that. It had 3,130. Our population table had 3,143. So why did we only get 3,036? Well, that's because in the pills table, there were listed some counties or places that were not actually in our county population table. And the reverse was true as well. There were also some places listed in our county population table that weren't in our opioid pills data because maybe no pills were shipped there, maybe it was an error, but either way, there was nothing in that table. Okay, so what got left out? What got left in? Well, we can use other kinds of joins to do that. So I want to talk a bit about left and right joins. So a left join is similar to an inner join in that what it's doing is it's looking for it's looking to put together two tables based on some shared column. An inner join, where an inner join only returned a record if there was a match in both tables. A left join is a little bit different. What it does is it says, give me all of the records from the first table that I'm talking about, and only show me those records where in the second table where there's a match with the first. But if there's not a match with the first, let's leave it out. So I just want to go back to the sort of Venn diagram here before we run this function. This is kind of what it looks like, right? It's saying, give me all of the records from table A, and only give me those records from table B, like match them up, if there's a corresponding record in table A. But if there's nothing, but if we have a record that's in table B but doesn't have a partner in table A, leave it out. Okay, so I'm going to run this. I'm going to store this as a new object called pills population left. And here it is here, right? So we have 3,130 observations, records, right? Notice, by the way, that's the same number as our original pills table. Remember, we're putting together pills and population. And this new thing we created with a left join has the same number of records as the original pills table. So let's go ahead and look at it. Okay, so just like before, right, we've got a lot of cases where there was a match on the county FIPS code, and it put together the average pills per year for this county with the average population per year for this county. Okay, all's well and good. Seems really similar to the inner join so far. I'm going to scroll down though. As we get closer to the bottom here, I want you to look at what's happening, right? So if you remember, in our original pills table, we had a bunch of records where it was just the state and pills. There wasn't a FIPS code. There wasn't a county. We also had a lot of cases, mostly in Puerto Rico, where you had the county and the state and the average pills per year, but no FIPS code. Okay. In the inner join, this is where our table stopped, right here on Weston, Wyoming. None of this information below was included. But because we did a left join, what we said was, give me everything. Give me everything from the pills table, even if it doesn't match with anything from the average population table. Which is why, as we scroll down here, everything is filled, things are filled in here, right? This is the data as it was represented in that original table. But all of this is blank. But because we did a left join, we can see all of the cases where there is no corresponding match. So why would you use this? Well, sometimes there are good reasons for wanting to have everything here, even if it doesn't match something in another table. You know, maybe we're interested in Puerto Rico, and we still want to see those results, even if we don't happen to have that information. It can also be helpful in sort of debugging, right? Like a thing I always look at to make sure my joins are going correctly is, am I getting the number of records that I'm expecting? And if the answer is no, I'll usually go back and use a left and right join to figure that out. And in this case, it seems to be, why was the number when I did an inner join smaller? Well, there's all this data that didn't have a FIPS code. Okay. So that's a left join. As you might expect, there's also a thing called a right join, which is the exact opposite of a left join. So if we go back to our Venn diagram, this is a right join, right? So in this case, table A, again, is pills. Table B is population. What a right join says is, give me all of the records from population, even if there is no corresponding example, matching example in the pills table. And give me only those records from the pills table where they match up with the population table. So here, creating a new object called pills population right. Got county pills per year is the thing that we are right joining with population, and we're again doing it by FIPS. So I run that. Okay, get a new table here. Note that it has 3,143 observations, which should come as no surprise, is the same number as the original population table. And when we look at it, we've got, here's our average population, right? So we scroll down closer to the bottom. Yeah, here we go. Trying to find something to sort on here. Actually, let's go ahead and run that one more time. So I'm going to go ahead and run that. Okay. Okay. So actually a pretty easy way to look at this would be just to sort by average population per year. And you'll notice, right, here's a county called Loving, Texas. This is its FIPS code. It only has 69 people. And remember, this is from our master population list. There is no corresponding pills shipment data for this county, probably because it's so small. If only 69 people here live here, the likelihood of there actually being a pharmacy is probably pretty slim. So this is part of the reason why, right? There are a lot of counties that actually had no records of shipments being sent to them, which is why when we do this right join, we still get it returned, even though there's this missing data. Okay. Okay, so we've done inner joins, which return only when there's a match. We did left and right joins, which return all the records from one table, even when there's not a match, return all the records from one table, even when there's not a match in another table. Now I want to talk about full joins, also sometimes called full outer joins. And it's kind of a combination of a left and right join. And what it says is, return everything from both tables. If there's a match, then go ahead and match them up. If not, just leave the alternate rows blank. So in a Venn diagram, this is kind of what a full outer join looks like. Give me everything from both tables, and where there's a match, match it up. So we're going to do one of those below. So the code below creates a new table called pills population full. So let's go ahead and open it up and take a look. And this is it right here. Notice it's got more records than any of the previous tables, right? So it's joining two tables that had 3130, and that's for the, just the table of pills by county. Population had 3143. when we do a full outer join, we get 3237. And the reason is that it's saying where there's a match them up, right? Autauga, Alabama was in both tables, and so it put it together based on the FIPS code. But as you'll see as we go down, there are examples in here. We can look at it pretty easily by sorting by average population per year, right? As we just saw in the last example. Here's an example of a county that was in the population table, but was not in our PILS table. And if we look at the other direction, we should see some of those as well. So let's sort by FIPS. Okay. And remember, here's some of the examples we were looking at before, right? Where we had a value for like a region in Puerto Rico for which we have no corresponding population data. It's in the PILS data, but not in the population data. So why would you ever do a full outer join? Well, sometimes it's useful to have just a full list of all information, but it's also sort of a quick way to see by just examining these NA values or missing values, what's in one table that's not in another table. Okay. My guess is that as you do more and more data journalism work, the things you'll probably use most frequently are inner joins or left joins. Okay, so one other thing I want to talk about is the difference between what are called one-to-one joins and one-to-many joins. So in the examples we did above, we set out to match a single record from one table with a single record from another table. We were trying to take the population information about a single county and match it to the PILS sales in a single county. Okay, so one-to-one, right? We're not looking to match one record to many other records. But there are times when that's exactly what we want to do. We want to match a single record in one table with multiple records in another table. This is the kind of thing that happens all the time when we work with multi-table databases that, for efficiency's sake and good database design practices, will store different but related types of information in multiple tables. So I just want to look at an example here of that. So the first thing we're going to do is we're going to load in a new table. This is in our data folder. It's called Mingo Buyer Per Year. And this includes one record per buyer, typically a pharmacy, per year in Mingo County, West Virginia, with the total of pills received in that year for each one. There's identifying information. The only identifying information about who the buyer is this unique ID or buyer DEA number. So I just want to run that, and then let's go ahead and take a look at that. So I'm going to pop that open. Okay. So again, each one of these represents the total number of pills sent to one place, typically a pharmacy, but also sometimes a practitioner, per year. So this pharmacy, AA, which is identified by the only bit of identifying information in this data, buyer DEA number AA8151728. In 2006, it got 279,800 pills. In 2007, it got 252. 2008, it got 219. 2009, so on and so on. So there's one record per year, typically, for each place. But the only way we know who this is by this buyer DEA number, which really doesn't tell us a lot. Okay. So again, this table, multiple records per buyer. Okay. The identifying information that we might want is stored in a separate table, and this is called Mingo buyer addresses. That's in our data folder, and you can load it by running this bit of code here. So we're going to run that, and we're going to go ahead and pop this open. Okay. And so what we see here, this is frequently called a lookup table, in which the information about each pharmacy, there's one record per buyer DEA number, has the name, the address, the city, the state, the zip, and other information. Okay, so our goal here in doing this join that we're about to do is to take the information in the buyer table, and each time in the buyer per year table, our goal is to take the information in the address table, and each time we see the buyer DEA number from here, when we see it over here, mash these together so that we're creating a single table that contains essentially all of this information. What that's going to mean, though, is the information in here is going to be repeated multiple times when we do this join. So let's go ahead and do this. So I'm creating a new table called Mingo buyer join. I'm taking the Mingo buyer per year table, this guy right here, and I am doing an inner join with the information here. Let's go ahead and run that. And I'm going to go ahead and pop it open. And now what we see here is we've got this original information about the transaction, right? Here's this AA8151728. This is the DEA number. This is how many pills in 06. This is how many pills in 07. This is how many pills in 08, 09, right? But to each one, we now have the name of the pharmacy. That's Adkins Pharmacy. Because this is the same number, this is also Adkins Pharmacy. This is the same number. This is also Adkins Pharmacy. It only appears once. The information about Adkins only appears one single time in our addresses like lookup table, right? AA8151728. When we joined it together, because it appears, this DEA number appears 6 times in our buyer per year data, it matches it every time. It says, I found the DEA number, put this information. I found the DEA number again, put this information. So it's important to know that when you are doing joins, if you have a unique value in one table, but in another table it's not a unique value, it appears many times, it's going to match it every single time. This is what we wanted to happen in this case, but there are also times when a failure to understand this means things will turn out poorly and not do exactly what it is you want them to do. So I want to look at an example of this, an example of how things can go sort of poorly or not as you expect. And we're going to go back to the data we were using in the section on left, right, and full joins above to do this. Which is to say, we're trying to do a one-to-one match, right? We want to match county pills per year, so the number of pills that on average went to each county between 2006 to 2012. And we're going to inner join it to our county population per year table, right? Because maybe we want to be able to redo and readjust recalculate the rate. Okay. I'm going to store this as an object called pills population. Oops. This time, instead of joining by FIPS code, which was a truly unique value that did not repeat in either of our data sets, we're going to join it on buyer county. All right. So above, we ran this, but we joined on the FIPS code. Now we're joining on buyer county. All right. And here's our pills population. Oops. And we get 14,716 observations. which is like way out of range of the 3,000 that we were getting in previous ones. Which is an indication that something went wrong. That when we were expecting a 1-to-1 match, what actually happened was a 1-to-many match. So let's go through what might be happening here. To make it a little bit easier to see what's going on, I want to add a filter to this. So this is the same function as above, but I just want to filter by Bexar County equals Montgomery here. And we're just going to look at Montgomery counties in our data. Okay, so I just reran that. Let's go ahead and reopen Pills population. Oops. I'm going to pop that out so we can look at it. It's got 3,000 records. Okay, so what's going on here? Well, to start, Montgomery County is actually we know most of you probably are familiar with the one in Maryland or possibly Pennsylvania, but there are actually 17 different states that have Montgomery County, meaning it's not unique in our data set. And because we're trying to join on something that's not unique, we're expecting a 1-to-1 match, but that's not what happens. So let's look at what's happening here. So let's start with the first row. And this actually worked out kind of as we were hoping for, right? This is on this side of the data is the data information from our average pills per year. On this side is the information about population. So it joined on this FIPS code, right? And Montgomery County, Alabama, was joined to the Montgomery County in Alabama. Good, that's correct. Okay. Now let's go to the next line. So we've got the average pills for Montgomery, Alabama, but it matched it with the population data from Montgomery County, Georgia. That's not good. Did it again, but for Illinois and for Indiana and for Iowa and Kansas and Kentucky and Maryland. Okay. Then let's go through all the Alabamas 17 times. So it matched the county for Montgomery, Alabama with the Montgomery County in 16 other states. Now we get to Georgia. All right. So it starts by matching the Montgomery County, Georgia with Montgomery County, Alabama. Not good. It matches Montgomery County, Georgia with Montgomery County, Georgia. Good. And it does Illinois. Not good. Indiana. Not good. And so on and so on. It cycles through every state. So instead of having a 1-to-1 match for each county in each state, by just joining on the county name, we created this pretty major problem. So something to keep in mind as you are doing joins. Think about unique values. Think about how to solve problems. You'll be doing these things over and over again. So definitely something worth thinking about. Okay, we're ready to submit. There weren't a lot of tasks for you to complete this week. So all you're going to do now is save the R Markdown file, knit it to HTML to make sure it compiles correctly. Then you're going to upload it to GitHub as instructed, and then provide links to GitHub in Elms.